Module 12.1. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 12.1. Now that we know how to collect sample data and how to describe the data, how can we use it to learn about the population? In previous modules, we discussed how to collect sample data and how to summarize data. In this module, we're going to look at how to take that information contained in a sample to learn about a population. Why do we use sample data to learn about population data? In many situations, the aim of a study is to learn about a population of interest. Unfortunately, collecting data from every element in a population can be difficult. Instead, researchers will take a subgroup from the population, known as a sample, to examine. Definitions. Previously, we saw these 4 definitions. Make sure to review them. In this module, we are going to begin to develop a set of tools that will allow us to take the information contained in the sample to say something reasonable about what is occurring in the population. We will accomplish this by studying the behavior of the statistic and see what the behavior of the statistic suggests about the parameter. Notice that the parameter is the information we really want, but we usually only get to observe the statistic. It is vital at this point to emphasize that vocabulary and notation are essential for this course. Make sure to keep track of the definitions and ideas. Previously, we already saw notation for different types of statistics and parameters. Values calculated from sample data are statistics, and values calculated from population data are parameters. We can summarize the information in a table. Looking across the rows, we notice that each statistic has a corresponding parameter and vice versa. For example, looking at the mean, a mean could be calculated from both sample data or from population data. When a mean is calculated from sample data, it is a statistic, and we denote this particular statistic with the symbol X bar. A mean could also be calculated from population data. When we calculate a mean from population data, it is a parameter, and we use the symbol mu to summarize it. From this point forward, we can think of each statistic as being paired with a corresponding parameter. We're going to learn how to use the value of a statistic to say something reasonable about the corresponding parameter. Most of the time, we cannot collect population data, and since parameters are calculated from population data, we cannot calculate parameters directly. In cases where population data cannot be collected, we can only learn about parameters via the statistic, which we can calculate. For example, again looking at the mean, the goal will be to use the sample mean X bar to say something reasonable about the population mean mu. Previously, we defined statistical inference as the process of using the information contained in a sample to draw conclusions about what is happening in the population. Now we can be even more specific. We can think of statistical inference as the process of drawing conclusions about the unknown parameter based on the calculated statistic. When we say unknown parameter, we mean that the value of the parameter is unknown. Carefully read each of the scenarios and identify the parameter and the statistic. For each scenario, give the notation and value if the value is known. The first is solved for you. The Kentucky Derby started in the year 1875. Data from all the winners of the Kentucky Derby can be found at the link given in the script. The average winning time for all winners is 129.28 seconds. A random sample of 20 winners was selected, and the average was found to be 131.45. Previously, in the worksheets, you saw this example. Notice here the population is all the winners of the Kentucky Derby. Therefore, the parameter is the average running time of all winners. The appropriate notation and value are mu is equal to 129.28 seconds. The sample is the selected 20 winners. The statistic is 131.45, the average running time of the 20 selected winners. The appropriate notation and value are X bar is equal to 131.45 seconds. Take a moment and pause the video and see if you can answer the next two. As of 4/28/18, NBA teams in the playoffs had an average of 94.25 points scored in a playoff game. Consider the data up to 4/28/18 to be sample data, and we are interested in all of the games during the 2018 playoffs. The population is the games played by NBA teams in 2018 playoffs. Therefore, the parameter is the average of points for all games. The appropriate notation is mu, and the value is unknown. Notice in this case, the value is unknown, but we can say in words what the parameter is. The sample is the games played up to 4/28/18. Therefore, the statistic is the average points per game up to that date. The appropriate notation and value are x bar is equal to 94.25. According to the link given in the script, a typical bag of M&Ms is about 13% orange. You would like to learn if there is a difference in the proportion of peanut M&Ms that are orange and the proportion of plain M&Ms that are orange. Out of a sample of 200 peanut M&Ms, you found that 26 were orange, and out of a sample of 200 plain M&Ms, 14 were orange. For this example, there are two populations, all peanut M&Ms and all plain M&Ms. Therefore, the parameter is the difference in the proportion of all peanut M&Ms and plain M&Ms that are orange. The appropriate notation and value are p subscript peanut minus p subscript plain, which is equal to 0.13 minus 0.13, which is equal to 0. There are two samples, the 200 peanut M&Ms and the 200 plain M&Ms. Therefore, the statistic is the difference in proportions of the 200 peanut M&Ms and the 200 plain. The appropriate notation here are p hat peanut minus p hat plain, which is equal to 12 divided by 200. Do we know anything about the behavior of statistics? If we are going to use statistics to learn about parameters, we need an understanding of how statistics behave. Previously, we discussed random samples. It ends up that if we select the sample randomly, we can say a lot about the behavior of statistics. To illustrate how statistics behave, we will start with an example where we have access to population data. We will be looking at the winning race times for the Kentucky Derby since 1875. First, we will summarize the population data. We will start with a dot plot of the population data. This is also known as the population distribution. Looking at the distribution, the mean winning time is mu is equal to 129.28 seconds with a standard deviation of 12.71 seconds. Also, notice that the distribution of the population data is right-skewed and bimodal. We have one mode here to the left and a smaller mode here to the right. Next, we will take a look at a random sample of 30 race times and look at a plot of the sample data. The mean winning time for this sample is 131.51 seconds with a standard deviation of 14.89. Also notice that the distribution of the sample data is right-skewed, and the overall shape is similar to the shape of the population distribution. This is known as the data distribution. Notice that this distribution, again, is right-skewed. We have a mode here to the left and a very small mode here to the right. So we can say that the shape of the sample distribution and the population distribution, while different, is similar. Next, we will take a second random sample of 30 race times and look at a plot of the data from the second sample. The mean winning time is equal to 130.38 seconds with a standard deviation of 14.41. Again, the distribution of the sample data is right-skewed and the overall shape is similar to the population distribution. We see that when we take random samples from the population data, we typically end up with sample data that is similar in characteristics to the population data. Earlier in the course, you were able to work with this data set and find something very similar. Our goal is to learn about the behavior of the statistic. For this example, the statistic we are interested in is x bar. Notice that the value of x bar was not the same for each of the samples. In the first sample, x bar was equal to 131.51, and in the second sample, x bar was equal to 130.38. Further, neither statistic was exactly equal to the parameter mu, but all values were close to one another. Definitions. Sampling variability is the change in the value of the statistic from sample to sample. Sampling error occurs when the statistic is not equal to the parameter due to looking at a sample instead of a population. Next, we are going to continue the process of taking samples from the population and calculating the statistic from each sample. This will need to be repeated for a large number of samples. We will look at 5,000 samples. Visually, for our example, we have the following. Notice that the population is all Kentucky Derby winners. We are going to take 5,000 samples. Each of the samples is smaller than the population, but similar in characteristics. From each of these samples, we're going to calculate an X-bar. Notice that this will result in a list of 5,000 X-bars. Notice that we have a long list of statistics. We know that the value of the statistic will vary from sample to sample. The parameter, mu, does not change from sample to sample. It is a fixed value. Mu is equal to 129.28 seconds. We can visualize the statistics calculated from 5,000 samples by plotting them in a dot plot. Notice the plot of the 5,000 statistics is symmetric and bell-shaped. Also notice that the plot is centered at 129.28, the value of the parameter. This plot is helping us visualize what is known as the sampling distribution. Definitions. A sampling distribution is the distribution of a sample statistic computed for different random samples of the same size from the same population. A sampling distribution consists of all possible statistics and how often these statistics occur. It helps us visualize how the sample statistic varies from sample to sample. The above simulated sampling distribution was created as a dot plot. We could have just as easily used a histogram. When a distribution is bell-shaped, unimodal, and symmetric, with mean, median, and mode at the center of the peak, this data comes from a normal distribution. Properties of sampling distribution. Center. If samples are randomly selected, the sampling distribution is centered at the population parameter. Shape. For many common statistics, the sampling distribution will be symmetric, unimodal, and bell-shaped if the sample is large enough. In other words, many statistics are normally distributed if the sample is large enough. There are other possibilities such as t-distributions, f-distributions, and chi-square distributions. We will look at these in later modules. Note, if you take random samples, the sampling distribution will be centered over the actual population parameter. If bias exists, in other words, if you do not take random samples, your sampling distribution may give you wrong information about the parameter, and it may not be centered at the value of the parameter. Remember, we are trying to understand how the statistic behaves from sample to sample. We can summarize the behavior similarly to how we summarize data in previous modules. The sampling distribution is a plot of the statistics and provides a visual summary. Numerical summaries are also useful. We can look at the mean of the statistics and the standard deviation of the statistics. The standard deviation of the statistics is important because it will help us assess the uncertainty of a statistic in estimating the parameter. In other words, it helps us describe how the statistic changes from sample to sample. The variability of the sample statistic is so important that it gets its own name. Definition. The standard error of a statistic is equal to the standard deviation of the statistic. The standard error measures how much the statistic varies from sample to sample. The standard deviation of the sampling distribution is also equal to the standard error. As the sample size increases, the standard deviation of the statistic tends to decrease, and the statistics tend to be closer to the true value of the population parameter. Therefore, small sample sizes will produce a sampling distribution with large standard error. Large sample sizes will produce a sampling distribution with small standard error. How do we know that the sampling distribution will be normally distributed for certain statistics? There is a fundamental theorem in statistics that informs us that the sampling distribution for the statistics given in this table will be normally distributed under certain conditions. The central limit theorem can be applied to describe the behavior of each of these statistics when repeated random sampling is performed. We will look at the central limit theorem for each of these statistics. Central limit theorem for a single proportion. When choosing random samples of size n from a population with proportion p, the distribution of the sample proportions has the following characteristics. In other words, what we're describing is the behavior of p hat. Center. The mean is equal to the population proportion p. The standard error can be calculated using the formula given. And if the sample size is sufficiently large, this distribution will be reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. When we say sample size, we're referring to the size of each of the individual samples that are selected. A normal distribution is a good approximation as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, which is the same as having an expected count of at least 10 in each category. It should be noted here that different texts may have a requirement other than 10. Central limit theorem for a single mean. When choosing random samples of size n from a population with mean mu, the distribution of the sample means has the following characteristics. The center of the mean is equal to the population mean mu. The spread, or the standard error, can be calculated by using the formula given, and if the sample size is sufficiently large, the distribution is reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. A normal distribution is a good approximation as long as the sample size is larger than or equal to 30. If the population data is normally distributed, the sampling distribution will be normal for smaller sample sizes. The sample size requirement of 30 is a general rule, and other text or resources may use a slightly different number. Central limit theorem for difference in proportions. When choosing random samples of size n1 and n2 from two populations with proportions p1 and p2, the distribution of the difference of proportions has the following characteristics. The mean is equal to the difference in the population proportions, p1 minus p2. The standard error can be calculated using the given formula. If the sample size is sufficiently large, the distribution is also reasonably normal. A normal distribution is a good approximation as long as the following four conditions are met. This is the same as having an expected count of at least 10 in each category. Again, it should be noticed that different text or resources may use a slightly different number than 10. Central limit theorem for a difference in means. When choosing random samples of size n1 and n2 from two populations, the distribution of the difference in means has the following characteristics. The mean is equal to the population difference in means, mu1 minus mu2. The standard error can be calculated using the formula given, and if the sample size is sufficiently large, the distribution is reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. A normal distribution is a good approximation as long as each of the sample sizes are greater than or equal to 30. The normal distribution is also a good approximation if each of the two population distributions are normal. One of the most important parts of the central limit theorem is the sample size requirements. The sample size requirements given are general guidelines. Other resources may use slightly different requirements. To predict the behavior of the statistic, we need the sample size to be reasonably large. Many people think that a sample needs to contain hundreds of thousands of people before we can make valid inference. Notice that the required sample sizes are much smaller.